Alright guys, let's get started on biochemistry. I want to start off with a story. This right here is mercury. You've all probably heard of it before. It's pretty cool actually. It's unique in a bunch of different ways. One way is it's the only metal that's liquid at room temperature. But I want to tell you a different story than that about it. I want to tell you about the Lewis and Clark expedition. You've all heard of this before. And I think the neat story about this is, as Lewis and Clark were getting ready to go on their trip, they knew they'd be eating a whole bunch of different foods on their trip, and so they were a little worried about having some digestive problems. Constipation is what they were really worried about. And so a doctor they knew sent them with a large pill that was essentially just like an enema. It would clean out their systems if they got constipated, and it was made of mercury. All right, here it is on the periodic table. It's Hg, and so they would take this whenever they were feeling a little rough. So the unique thing about this is, many years later, when we wanted to retrace their steps, where they went, where exactly their trail was, the Lewis and Clark trail, all they had to do was basically use a metal detector and find the mercury, because we could follow where their bathrooms were, their latrines, all the way across the United States. So this is kind of a neat story to get started on biochemistry, since we're going to be talking about the chemistry of life quite a bit, and that's one of those stories you can maybe remember for a long time and tell to someone else. I want to start though by doing a little review of probably some of the stuff you may have done last year a little bit, and talking about just chemistry in general. And of course, whether it's mercury or any atom, we need to start by talking about the atom itself. And I want to start going over the pieces and parts of an atom. So, alright, so the pieces and parts of an atom is what we're going to start talking about here. And let's start by labeling them. This right here are the electrons floating around the nucleus of the atom. The electrons have an overall negative charge. This is pretty important because inside the nucleus are the protons, and they're what keep the electrons in orbit around, because they have an overall positive charge. So these two will attract each other. Alright? The other piece are the neutrons, which have an overall neutral charge. No charge at all. So these two are really the most important. Neutrons just add extra weight to the atom. Protons are the overall positive charge. Electrons, the overall negative charge. Electrons are especially important because they ultimately cause, in a lot of cases, cause atoms to bond to each other. So what I like to do when I'm trying to figure out what everything has, I like to write out PEN, pen, protons, electrons, neutrons. In this case here, I count 6 electrons. If you look on the inside, if we say the blue ones here are the protons, there's 6 protons. And 1, 2, 3, 4, 5, 6. 6 neutrons. Alright. Now, since that means there's 6 positive charges and 6 negative charges, the overall charge of this atom is 0. All the positives balance out all of the negatives. Right? If I were to strip away one of these charges, if one of these electrons went floating off into space, so that I only had 5, then I'd have 6 positives, 5 negatives, an overall +1 charge. Now, if I had a +1 charge, then I'd give this atom a special name. We call it an ion. That means it has a charge. It could happen the other way too. I could keep those electrons and I could have an extra proton, right? And then I'd have, or I'm sorry, I could lose a proton, let's say. There we go. then I'd have only 5 protons, 6 electrons. I'd have an overall negative charge, -1 charge. That's also called an ion. So here are the Maggie Sponge Cafe. This is a little mnemonic device to help you understand all the chemicals, the most abundant chemicals important to human life, or to not just human life, but life in general. Maggie Sponge Cafe. This stands for, let me write this all down, Maggie's is magnesium. Sponge, kind of a weird word. They each have their own meaning. Sulfur, phosphorus, oxygen, nitrogen. Alright, here's the king carbon, very important to life. Hydrogen. And the cafe, Ca stands for calcium, and Fe stands for iron. So those are the, let's see, what's that, 3, 6, 7, 8, 9, probably most abundant and most important chemicals to life. And we'll probably talk quite a bit about many of these throughout the year. That's a good little way of remembering the most important ones. Maggie's Sponge Cafe. Now, what I want to do next is start talking about just overall what the way we can symbolize and talk about these chemicals. So let's start with chemical symbols. Very simple. We do all chemical symbols, let's come over here, with a capital. A capital C, for example, is carbon. Right? A capital O, oxygen. You guys know this. Now, if sometimes we have more than one letter in a symbol, what we do is we put a capital and then any letters after that are lowercase. CO would be cobalt. That's important to know because if you put a capital C and a capital O, that is actually carbon right here bonded with oxygen right here. Right? Big difference between cobalt and this one. This is called carbon monoxide. Right? This would kill you. Right? Breathe this in small amounts and you go to sleep and you don't wake up. You guys are more familiar with this one, CO with a 2 after that. That's the way this is written. It's telling me that we have 1 carbon and 2, let's see if I can spell that right, oxygens. And that's carbon dioxide, 2 oxides. Right? So I want you to understand how we write compounds and molecules when we put these little subscripts. That means it's telling you the number of that particular atom. So here's one that you'll see this year quite a bit. C6H12O6. That's sugar. We call it glucose. We'll be learning about that very shortly. Another lecture or two. What we have here, 6 carbons, 12 hydrogens, and 6 oxygens all bonded together. Alright, so far so good? Alright, what I want to talk about next is the bonding process itself. And there's 2 really important types of bonds that I want to talk to you about. The first one is called the ionic bond. Alright, there we go. The ionic bond is when you have a metal that is bonding with a non-metal. An example. Classic example, a lot of people always talk about this one. Sodium is a metal. If you bond that with a non-metal called chlorine, you have sodium chloride. Right? They bond together here to make NaCl. So that's an example of an ionic bond. We can get into the details here, but I'm going to keep it kind of simple for the time being, just by saying that the way they bond is this sodium will give, this sodium will give one of its electrons to the chlorine, and that creates an ionic bond between the two of them. All right. So what you're going to end up having is an ion of sodium and an ion of chlorine. This is going to have an overall positive charge. This is going to have an overall negative charge, and that's going to cause them to link right together, an ionic bond. All right, the other example, other type of bond that's really important is a covalent bond. We'll underline this one, we'll underline this one. Covalent bond is between a nonmetal and another nonmetal. Very common one. Here we go. If you take two hydrogens and link it to one oxygen, you have a very important covalent bond, H2O water. Here, instead of an electron being given away, they share electrons. Like one electron going around hydrogen will start going around the oxygen, and vice versa, and they'll share those. All right, so that right there is a covalent bond. We'll be talking about these two types of bonds a lot. But before we go there, as we talk about these, you kind of have to know and understand how chemical reactions are written. So I'm going to write an ionic bond so you can see what happens. And this is going to be simplified, meaning I'm not going to get into a lot of detail on balancing this equation. If we take an atom of iron and we put it in the same room with an atom of oxygen, they will bond together to form iron oxide. Right? That's like your rust. So in a chemical reaction, we call these on this side the reactants. They're going to react with each other to form a product. So this side over here are called the products. So you have reactants, products. This little arrow here, oftentimes people like to say yield. If you put these two together, it will yield this. It will make. Right? Sometimes you see them written so there's an arrow going both ways. And what that simply means is this reaction can happen this way, or it can be undone and happen this way. Either way, depending on the circumstance. Right? So we have kind of a primer here on all that stuff, and I want to show you something.
It's practically standing still now. They've dropped ropes out of the nose of the ship, and it's been taken a hold of down on the field by a number of men. The back motors of the ship are just holding it just enough to keep it. It bursts into flames. Wait, get it started. It's fighting, and it's crashing terrible. Oh my, get out of the way, please. It's burning, bursting into flames, and it's falling on the morning fast, and all the folks believe that this is terrible. This is the worst of the worst catastrophes in the world. Oh, it's 400 or 500 feet into the sky, and it's a terrific crash, ladies and gentlemen. The smoke and the flames now, and the flame is crashing to the ground, not quite to the mooring mast. All the humanity and all the passengers screaming around it. I told you. Never talk to people whose friends are on there. I can't talk, ladies and gentlemen. Honest, it's just laying there, massive smoking wreckage.
So that's I think a pretty cool video. It's just showing you, chemistry in action. It's unfortunate. That killed 35 people in that disaster. But about 2/3 of the people made it out of there. Most of the people who died from the actual fall, or from like bursting diesel fuel, kind of going everywhere. There's a story of one 14-year-old boy named Werner Franz who was on there. He actually was standing under a water tank that burst, and it came just washing down on him, put all the fire around him out, and that's basically just pure luck how he survived that crash without being burnt up or whatever, and was able to have enough sense when he landed to run in the right direction, which I have to imagine that'd be pretty complicated. You'd think it'd be easy to run away from the fire, but if it's around you everywhere, he actually made it out of there. All right, so let's change gears a little bit. We're going to look at a covalent bond, which is this right here, the hydrogen, two hydrogens and oxygen. And I want to talk about something else that's pretty important in biological chemistry called polarity. Polarity. It's a weird why. Polarity is the idea that some molecules, like water, have poles, sort of like the North and South Pole. This has a positive charge, this has a negative charge. Right? Oxygens have that negative charge. And because of that, this one has a negative charge, this one has a positive charge. These will get attracted to each other. It can be kind of the precursor of hydrogen bonding. Another type of bonding that is really important. It's what bonds your DNA together. So you can imagine it's pretty important. In class, I'm going to show you a little demonstration of polarity. But what you can really take away from this right now is that this is what causes other objects that have polarity to dissolve, like salt, the NaCl. This has a positive charge, this has a negative charge. Because of that, salt will dissolve in water. Sugar, anything that dissolves in water is because it's also polar, has polarity, just like the water. Oil, on the other hand, does not have a polarity. It has no overall charge on it. So when you put oil and water together, they stay separate. They will not mix. It's because you're mixing a non-polar material with a polar material. Like I said, I want to show you a little demo in class to show this to you. But let's move on from here for now. Another thing you're going to really need to understand has to do with acids and bases. And we'll spend a little time with this as well. And what I want to get across to you is the effects of acidity in life and in the environment. You can see how acid rain has worn away the statue over time. You have certain parts of your body that have acidity. Your stomach is very acidic. It's pretty important that your stomach is acidic. It helps to destroy harmful bacteria that you may have ingested with your food. If you're not careful, your blood can become too acidic, and we go through that process of homeostasis to keep your blood from becoming over acidic. And it's when we talk about acidity and how something is acidic, what we're really looking at are these molecules existing in a solution, maybe in water. This right here is called a hydronium. It's just 3 hydrogens and an oxygen bonded together, and it's ionic. It has this positive charge. And this over here is a hydroxide. OH negative, has a negative charge. When these exist in solution, it is ultimately what is going to tell you if that solution is acidic or basic. All right? Another word for basic or base is alkaline. So the more you have, the more concentrated your solution is with hydronium ions right here, the more of those that are dissolved in your solution, the more acidic your solution becomes. You could have something like battery acid, sulfuric acid, so acidic it could eat right through your clothing. And the less these have, the more basic your solution is going to be. And that also can be very dangerous. But on a pH scale, let's write that up here, little p, big H, it tells you how acidic or how basic something is. 7 is the magic neutral. It's not acidic, it's not basic, it's right in the middle. Anything that goes below 7 up here is acidic. And the further down you go, the closer you go to 0, the more acidic it is. Alright? Going up from 7 are your bases. And again, the further away from 7 you get down here 13, 14, the more basic it is, the stronger it is. Okay, so that's just kind of a good way of thinking about acids and bases to get started. So when we go over that in the future with future labs or discussions, you'll understand what I'm referring to. The other thing I want to talk about are buffers. B-U-F-F-E-R. A buffer is basically something that can control how acidic something is. If you have a really high acidity, really super, like all these pluses means it's acidic, and you put a buffer in and it moves through that, what it'll do is it'll reduce the acidity, make it not as acidic. It'll kind of soak that up like a sponge. Alright, I wanted to use an analogy. An analogy means a comparison. This kind of buffer is very similar to what we call a riparian buffer. Riparian buffers are a little different. They're dealing with nature and not just buffering out acids, but buffering out all kinds of pollution. But it does the same thing. It buffers. It reduces the acidity, or it can reduce how basic something is. And here's how a riparian buffer works. If you get all this pollution dumped right here, and it comes flowing down towards the water, the trees will take some of that pollution up, and the bushes and the grasses, so that it becomes less and less and less, and only a little bit gets into that water. It kind of takes the pollution out. Well, buffers that I'm talking about are similar to that. They're just reducing how acidic or how basic something is. And I'm going to end our discussion there, and we'll be doing a lot of work on this in class, and I'll see you then. Bye-bye.